We want to now look at a series solution method for second order differential equation, and this is a way to try to understand the nature of the behavior of the solution locally near some point of interest. And so let's remind ourselves of the equation that we are interested in, second order variable coefficient linear ordinary differential equation, and we're going to be looking at the series expansion method for it. And so this is the general form of the second order equation with arbitrary coefficients here, p of x, q of x, capital Q of x, and capital R of x. And so we are interested in describing the behavior of the solution in the neighborhood of some point x naught, and we want to know how the solution behaves in some region near the point x naught. So for this, we have to distinguish two cases. Case 1 is when the point x equals x naught is an ordinary point. And so let's remember the definition of an ordinary point. Ordinary point of a differential equation is where this leading order coefficient here is not equal to 0. And of course, at such a point, we are assuming that these other coefficients that we have are not blowing up or anything. They are also well-behaved functions and so on. So everything is just regular ordinary behavior with this leading order coefficient not vanishing. All right? And so the way we will proceed is we will then divide the equation by p of x, and so clear it, move it to the denominator, and so we'll then have this equation y double prime plus little p of x times y prime little q of x times y equal to 0, where little p and little q are defined by those ratios that you can immediately see. All right, and so we'll assume that since we have ordinary point, p is well behaved near x naught, and so p x naught equals p naught, and q at x naught is equal to some number q naught. Given this, we can also do a Taylor series expansion of these two functions p and q around the points x naught, and so we therefore have this Taylor series expansion of p, and we have a Taylor series expansion of q, and we can have more terms and so on to get more accurate series expansion solution. So this is the value of the function, this is its derivative times x minus x naught, and this is the second derivative x minus x naught over 2, and so on. And so this is a series expansion of the coefficients, and the next thing we need to do is to propose a solution for y, and then we will be in a position to work. So to proceed, we propose a solution for y of x in the region for x near x naught, and so we also have a series expansion for y, and so y is written as y at x0, its value, plus a series which gives us its variation, and so ak is a coefficient associated with x minus x naught to the power k, and this power series is summed from k equals 1, 2, 3 all the way up to as many terms as you want to go. If you want, we can put this term also inside here. This doesn't have any x minus x naught, and so we can call this a naught if you like, and we can put that in here and have the series go from k equal to 0 onwards and so on. This is just two different ways, equivalent ways of writing it. But having written the solution y of x, we can now differentiate this, and so if we differentiate it once, then we have a solution for dy dx, which has a series expansion. Of course, this is a constant, so it doesn't show up, and here we have a series, and so we can differentiate this series by differentiating each term and then summing it up. And so since we have power k here, when we differentiate, we get this power here, and we get a lower power for each term, and so that's the expansion of a derivative. And then we also can evaluate the expansion of the second derivative. And so now going to second derivative, we differentiate this once more. And so this k minus 1 comes up in front. And so we have k times k minus 1, ak x minus x naught, k to the power minus 2. And that's then the series solution representation for the function, first derivative and second derivative. And these appear in the equation, and so we need them. And so we substitute these in the governing equation, this ODE, and look at the coefficient at each power of x minus x0. In particular, we can look at x minus x0 to some power j, evaluate that coefficient and set that coefficient equal to 0 for each value of j, and that would be a system of equations for aj's which we can solve, and that would then give us the series solution. So that would be how we can find the behavior of the solution near an ordinary point. And so the next case that we will need to look at is the case when x equal to x0 is not an ordinary point, but it is a very special point, or it's a singular point. And so when it's a singular point, the value of p vanishes at x0, and for this there is a different method which is a variation on this scheme that we have talked about, and it's called Frobenius method. It's named after a mathematician named Frobenius, or this expansion will be called Frobenius expansion. And so we will next turn to describing this method which will give us a solution near the singular point. All right.